This paper presents a real-time falling robot stabilization system for a humanoid robot, in which the robot can prevent falling using hand contact with walls and other nearby surfaces. This following video shows that our system uses environmental obstacle geometry to determine a point of contact to stabilize itself from falling. The flowchart of the proposed system is as follows. Here we have four main components: fall detection, pre-impact optimal contact, post-impact stabilization, and push-up recovery. Fall detection monitors the robot state online with an inverted pendulum model and computes the orbital energy as the fall prediction indicator. The pre-impact optimal contact uses a direct shooting method with a heuristic start to compute the optimal joint trajectories to minimize the collision impact and necessary friction. After the contact, post-impact system will dampen the residual angular velocities with its own compliance. If the robot is not leaning too far after stabilization, push-up recovery strategy will use the elbow motion to generate a momentum to bring the robot back into an upright posture. Our system models the humanoid robot to be a 3-link rigid body. This video shows how to match the real robot geometry with the proposed model. We implement this system on a small humanoid platform augmented with additional sensors. IMU provides the information of the robot angles and angular velocities. Raspberry Pi 3 undertakes the computational task of the optimization. Touch sensor tells our system to switch into a post-impact stabilization system when a contact is detected. We test our system in many scenarios. Vertical walls are used for hand contact. We notice that the robot reaches its hands towards the wall to rest itself from falling, and reaching is further for walls at a further distance. In addition, we test our system in a waist-height flat surface. It is clear that our method can explore the flat table surface to stabilize the robot from falling. Flat ground surface is also used in our experimentation. Our method finds the optimal contact with the bent-over posture, in which the robot's center of mass remains relatively high above the ground to minimize the collision damage. A heuristic push-up recovery method is utilized in our experiment after the robot has already been stabilized. The robot will bend its elbow first and then stretch the elbow to generate a momentum in the direction away from the wall. These two examples demonstrate that the push-up recovery method can recover the robot to a standing posture and enable the robot to continue on its previous task interrupted by the push.